Welcome to LIMACON 2016. This is a re-recording of my presentation from Session A, Friday, March 11th in the morning at SUNY Old Westbury. I was speaker number 14. Let's see, which is Sage Advice, Calculus with CAS. So we're talking about using a computer algebra system, a CAS, okay? All right, so, and let's see here. So, what I'd like to do is welcome you all here. This is a little welcoming letter I gave out. Alrighty, and hang on. So, hello and welcome to LIMACON 2016. Thanks for coming. Please allow me to introduce myself. I've taught all levels of mathematics at Bolton Senior High School for 32 years and Nassau Community College for 21 years. I've taught programming since 1975, high school math, computer science, and physics since 1984, college math and computing since 1993, cluster programming since 2002, and scientific computing since 2011. So the way I teach math has evolved greatly over the last 10 years. For example, I've flipped my classroom. I've also been smartboarding and screencasting for at least 5 years, and I share all my smart notes and videos with my students on Edmodo, on Blogspot, and on YouTube. I'll show you my Blogspot in a minute. I've always been in the forefront when it comes to adopting new and effective technologies for use inside and outside my mathematics classroom. During the 1990s, I was one of the first to promote the use of graphing calculators in all math and science classes. However, I'm here today to tell you that we're in the midst of a whole new revolution in computing technology. These new computing environments include everything from computer algebra systems and programming languages to supercomputers and scientific computing. So today, I will speak about how I use Sage instead of graphing calculator in calculus class. Let me show you how I use a computer algebra system such as Sage to teach high school and college math curriculum. Okay, so what we're going to do is, if you go to my blog, there it is, you'll see that it's stored. By the way, that's a picture of my classroom over at Baldwin. Okay, anyway, you'll see that I've stored a lot of the materials for this session right here. Whoops, sorry, this is a little laggy. I'm controlling my smartboard remotely over Wi-Fi with my tablet. It's getting a little laggy there. But anyway, so there's the welcome letter, there's the brochure, and we're going to do all this stuff. Okay, so let's start. What if I go to a Sage cell? And let's just do some algebra to get used to the idea. All right, so let's say we let f of x equal x cubed minus 1, a difference of two cubes. All right, and let g of x equal x minus 1. Okay, and if I just say, let's see, hang on. How can I get this? I want to get this right around here. Okay. Now if I say show f of x, all it does is prints out what I typed, but in pretty print, like in a textbook, or like on a TI-89, that kind of thing. And f of x, or TI Inspire. Let's see. So if I just show both of these, click evaluate, and there you go. Good. So now, what do you want to do with this stuff? Well, what if you want to add them? All right. So what if I say, well, for the sake of space, let me just throw that here. What if I want to add those two, x cubed minus 1 and x minus 1? And what if I wanted to subtract them too, by the way? Well, I'm at it. F of x, f of x minus. Okay, now let's show that. So if you add them, don't you get x cubed plus x minus 2? And if you subtract them, don't you get x cubed minus x? There you go, perfect. All right, so that's adding, that's subtracting. How about multiplying and dividing? Let's see. Let's multiply and let's divide. Although I'm re-recording today because we had some technical difficulties. I ran out of hard drive space. Did I mention that? While rendering the video, so I really wanted to have a little video for you guys to review after the session, so there it is. Now that's great, but that's what computer algebra systems do. They give you answers in simplest factored form. Okay, so instead of x cubed minus 1 times x minus 1, I want to FOIL that out, let's say. How about we use the expand command? So this system, Sage, is based on Python, and it uses a lot of free Linux open source software to do the actual algebraic manipulations, okay? And all right, let's just see what happens if you FOIL it out. There you go. And what if you actually want to simplify this? We have to tell it to do that, all right? So you can put in parentheses what you want to simplify. Dot simplify. Now that's usually not enough. Sometimes you have to tell it if it's like a trig identity you want to reduce. You have to say simplify trig, or some kind of weird radicals or powers to simplify radicals. But this, I want to simplify a rational expression. And by the way, isn't x cubed minus 1 a difference of two cubes? So we know how to factor that, don't we? X minus 1 times x squared plus x plus 1. Let's see if that's what we get. There you go. And when we cancel out the x minus 1, we're left with the x squared plus x plus 1. Or I always tell my kids that factoring is dividing, right? So what if you say factor f of x? Whoops. Case sensitive, this is based on Linux, careful. Whoopsie. Alright, so if I factor it, I should get the x minus 1 times. Oh, I forgot to close my show. See where the green parentheses match up? I wanted these, right? Okay. And so the factors of x cubed minus 1 are x minus 1 and x squared plus x plus 1. Perfect, okay. What about exponentiation? Let's see. What if I do this? Show, I don't know, how about quantity, x plus 1 to the 0. Again, this is Python. The Pythonic operator for exponentiation is star star, like super multiplying, right? But they find that many people coming to Sage are coming from TI Basic, so they know that in the basic programming language they use a caret for this. All right, so what's I'm going to save some space and get rid of this stuff for now. Get rid of that. Okay, so what if I show that? Well, anything to the 0 is 1, right? Okay. What if I do to the 1, to the first power? Click evaluate, as you would expect. And to the second power. And well, right, well, fine, but what if you wanted to expand that? Okay, so expand. Okay. And that's what you would get, right? What if you want to do a whole bunch of these, sort of like a binomial expansion theorem? Well, we could write a little mini program, a little Python script for, let's say, n in range, I don't know, 5, colon. Now the colon is syntactic. When you hit enter, the tabbing is syntactic. It's actually 4 spaces. In many programming languages, whatever you put in a for loop has to be in braces. Well, in Python, it has to be indented, and anything that's anything else, any other lines that you want to repeat 5 times, have to be indented too. So look what you get if you make this powers of n, or the exponent is n, and you sort of get the binomial expansion theorem, like for free there. Oops, this is getting a little clunky. There you go. All right, so and the Pascal's triangle too. Look at the coefficients: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so forth. Okay, and you could get crazy with this. You could say, okay, how about we go up to, I don't know, 10. And by the way, range gives you integers starting at 0 and gives you, in this case, 10 of them, so 0 through 9. So these are powers of x plus 1 to the 0 through 9. And let's see, we can see some more of this. There you go. So this is pretty crazy. This is all calculated in real time in a supercomputer set up over at the University of Washington State. All right, so that's just giving you a little taste of, let's say, a little algebraic manipulation that computer algebra systems do. Now, let's get to the calculus. Okay, let's see. Do you know this clip? Let's see if you know this clip. Where is it? There it is.
Contestants, find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier. All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh crap, I lost.
That answer is incorrect. And we are in a sudden death. If Miss Heron can answer this problem correctly, we have a winner.
Limits, why couldn't I remember anything about limits? Limits, that was the week Aaron got his haircut. Oh god, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mathletes.
How you like me now? You like that? Yeah. Get some. Get some.
Whoops.
Contestants, fine.
Okay, so anyway, so the idea is, where did my blog go to? My blog disappeared. There it is. So here at the very beginning, here's the problem that she was doing. There you go. So the mean girls limit problem. So it was the limit as x goes to 0 of ln of 1 plus x, 1 minus x, minus sine of x over 1 minus cosine squared x. By the way, next year in AB Calculus, they're introducing the concept of L'Hopital's rule for the first time, aren't they? Well, this is an example of that. Look, this is not a plug-in limit, because if you plug in 0 for x, what do you get? So ln of 1 minus 0 is 1, ln of 1 is 0, okay? Sine of 0 radians is also 0. So in the numerator you have 0 minus 0 is 0. On the bottom, you have cosine squared of 0, and cosine of 0 radians is, again, 1. Squared is 1, and 1 minus 1 is 0 on the bottom. So this is not undefined necessarily, and if you get a limit that's 0 over 0, infinity over infinity, L'Hopital said, take the derivative of the top separate from the bottom, not, quotient rule, okay, and try again. And as soon as it changes from 0 over 0 or infinity to something else, you've got an answer. You might have undefined. If it changes from 0 to 0 to 0 over 2, it's 0. If it changes from 0 over 0 to 2 over 1, it's 2. If it changes from 0 over 0 to 2 over 0, it is undefined. Okay? So what's going on here? Well, the derivative of ln of 1 minus x is 1 over 1 minus x times the derivative. Well, see, now that's the thing. Shall we use Sage to do all this stuff for us? Okay? All right, let's do that. So let's get out of here, and let's get back to Sage. And let's see, we want all right, so let's say the numerator, let's make the f of x the numerator and g of x the denominator, and let's talk about this stuff, okay? So, the numerator was, hang on, okay. It was the ln. Now be careful, many upper level languages, even like Java and C, log is not common log or log base 10, it is log base c, it's ln. All right, so of 1 minus x minus sine of x, okay, and the denominator was 1 minus cosine squared, right? So 1 minus the cosine squared, and this means we're squaring the whole function, not just the x, okay? Alrighty, now, so for fun, just to evaluate that, what is f of 0 and what is g of 0? Okay, so f of 0, in fact, let's show it. Let's show f of 0. We said it would be 0, right? Where did my output screen go? There it is. And if you show g of 0, you also get 0, right? Okay. So what I want to do is find the derivative, okay? Now, if I want to show, just for fun, if I want to show f of x and g of x, I can do that too. So there's the numerator and there's the denominator, written sort of backwards, but there you go. Now, what if I don't want that? What if I want the derivative of that? So this is what you do. Take the differentiate, of f of x. Now this system is designed for higher level math too, not just calculus, multivariable calculus, right? There might be more than one variable, so you have to say what you're differentiating with respect to, so comma x. That's sort of like the dy dx part, right? And let's show the derivative of g. And see what we get. And so the derivative, of log of ln of x is 1 over x, right? But it's not ln of x, it's ln of u, it's chain rule. So you get 1 over 1 minus x times the derivative of 1 minus x, which is negative 1. So you get negative 1 over 1 minus x, which is 1 over x minus 1. And the derivative of the sine is the cosine. Good. The derivative in g, the constant 1, is 0. The derivative of cosine squared, or stuff squared, chain rule again, is 2 stuff to the 1 times the derivative of the stuff. With the derivative of the cosine is negative sine. So you got 2 cosine sine. There you go. Perfect. Now, what if you plug in 0 now? Let's see. So the numerator, if you plug in 0, is 1 over 0 minus 1 is 1 over negative 1 is negative 1. The cosine of 0 is 1. So you got negative 1 minus 1 is negative 2 in the numerator. Now, what do you get in the denominator? You get 2 times the cosine of 0, which is cosine of 0 is 1, times the sine of 0, which is 0. So you got 2 times 1 times 0 is 0 in the denominator. So you've got negative 2 in the numerator and 0 in the denominator. Negative 2 over 0 is undefined, so that was correct. Now, for fun, what if we use the limit command? Show the limit of f of x over g of x as x approaches 0. Alrighty, and I think I need another parentheses over here. And so let's see what that is. Okay, hang on. Evaluate. Whoops. And we get infinity. So there you go. So even the limit command agrees. And this does limits the normal fashion if it exists. You know, you can just, if it's a plug-in limit, it'll just plug in the function value. You can do limits from the left, limits from the right. I think you just do comma dir equals quote left. I think if you want the limit from the left. I think that's how it works. And if you have a vertical asymptote or horizontal asymptote, you might go to positive, negative, infinity, that kind of stuff. If you want to go to the right. Right, it goes to negative infinity. If you graph this, right, you have a vertical asymptote. From the right, it's going down to negative infinity. As we approach 0 from the right, as we approach 0 from the left, it's going to go to positive infinity. Why don't we, well, we could graph that and show that. Let's see, plot f of x over g of x. And see what that looks like. Whoops, what happened there? Whoa. And so there you go. So as x approaches 0 from the right, y is approaching negative infinity, and as x approaches 0 from the left, y is approaching positive infinity. There you go. And notice when you do a, let's see, can I move this around a little bit? No. All right, I'm sorry, I'm having trouble scrolling here from on the tablet. That should be on the desktop for this. All right, but notice you can't see it really, but the x-min and x-max default to negative 1 to 1. You could change that. What if I did a plot from, I don't know, something closer to 0, say from negative, I don't know, 0.25 to positive 0.25. Let's see what that looks like. Excuse me, my mouse is going crazy. There you go. And by the way, this is notation 2e to the 4. It really means scientific notation 2 times 10 to the 4th, which is what, 20,000? Okay, so you get the idea. All right, so that's a little bit about limits. It's a little bit about derivatives. Alrighty. What about the chain rule? Let's play around with the chain rule a little bit. What if I said, okay, let's start from scratch. Get rid of all this stuff. What if I say for n in range of 5 again, show the diff of, now let's see, what do I want? How about the sine of n times x? Okay, let's see. Now, do I have enough parentheses here? Yeah, it said don't forget, no, except don't forget to close the show, and don't forget, inside the diff, you have to say you're differentiating with respect to x or whatever your variable is, and let's see what we get. Does that make sense? Now, realize what we're doing. We're differentiating the sine of 0x. Well, the sine of 0x, the sine of 0 is 0. The derivative of 0 is 0. Okay. Then the derivative of the sine of 1x. Well, the derivative of the sine of x is cosine of x. How about the derivative of the sine of 2x? Well, the derivative of the sine of stuff is the cosine of stuff times the derivative of the stuff, chain rule, right? So this is a nice quick way to show how chain rule works. Make it even more interesting. How about instead of n times x, how about x to the n? What would you expect now? So this would be sine of x to the 0, sine of 1 is 0, and the derivative of the 0 is 0. Okay, the sine of x to the 1 is sine of x, the derivative of the sine of x is cosine of x. But look at this. The derivative of the sine of x squared is the derivative of the sine of stuff is cosine of stuff times the derivative of the stuff. Okay, there you go. Alrighty. And so forth. So that is a nice quick demonstration of the chain rule. And you can do all kinds of different versions of that. And you can demonstrate all kinds of different derivative rules and so forth. Just for fun, regarding the L'Hopital's rule, one of my students made a little song about this. We do calculus carols. We sing around. We go all over the school the day before calculus break. Christmas break, celebrating Newton's birthday, which was actually Christmas Day. And one of my students wrote this song, and it has to do with L'Hopital. Here you go.
Just see those limits are approaching, it's a 0, 0, and we can't figure anything, so what the heck do we do? Numbers full of memory, it's got a weird ratio there too, and we still can't prove it, so what the heck do we do? Up and down, let's go, let's solve it a pro, we're trudging in a nightmare. He's right, he's a right-hand man. He came up with the theorem that works, if you understand. No, he was really pissed, cause he knows that something exists. But then he jumped with me back in 1693. Let's take the derivative of the top and of the bottom one too. And if the limit don't exist, he still knows just what to do. Just keep taking the derivative there all day long. You'll get it right if you just join in and sing this song. It only takes a few steps, so let's try not to mess this up. He can swear to you the answer's just with Paul. Yep, I'll get what's wrong if you think that it's a deity. But the L'Hopital, you'll find that the solution's free. So all that fuss was for nothing because it's all easy. It's a wonderful theorem that I hope I still make you see. Just take the derivative of the top and of the bottom one too. And if it still don't exist, we now know just what to do. We now know just what to do.
I was a valedictorian that year. He was at the piano. He made the words. Michelle was the sister. She's on Broadway now. She's a singer, professional singer. And there you go. Okay. So, running a little bit low on time here. So, how about we just show... let's see, let me get rid of this. There you go. All right, so what about integration? How do you integrate stuff? Well, something simple. How about f of x equals x cubed minus 1 again? Or how about minus 2 times x squared plus x minus 3, say, okay? Be careful, in this system, and multiplication is not implicit. If you want to multiply, you've got to use the star. So what is the integral of that? Let's see, show, well, how about we do this? No, let's show, integrate, what are we integrating? F of x. Whoops. And again, you got to say with respect to x. That's like the dx, f of x dx. Okay. And let's see what you get. And did you expect that? The power rule, right? All right. And now, what if we wanted to show U-substitution? How does U-substitution work? Let's see. How about if I say for n in range 5, or whatever you like, let's show the integrate of, now let's think about this. How about sine of x to the n? Now think about it. If it's like x squared, you'd like to see a 2x up front, right? So how, or if it's x cubed, you'd like to see a 3x squared or something x squared up front. How about we do x to the quantity n minus 1 times that? How's that? Would that work? Let's see. And I'll get rid of this show. Let's get rid of this whole thing here. Okay, there you go. So let's run that. Alrighty, now see, I didn't really want to start with 0 through 4. How about if I do 1 comma? It'll still stop at 4, but it'll start at 1. So n starts at 1. So I'm going to have x to the 0, sine of x to the 1. So the antiderivative is basically x to the 0 is 1 times sine of x is sine of x. The antiderivative is cosine, right? But what if n is 2? Well, the antiderivative of x to the 1 times sine x squared, well, do u-substitution. U is x squared, du is 2x dx, replace the dx with d over 2, and that's where you get the 1/2. The negative came from the cosine. And so forth and so on down the line. So you can quickly show how integration by parts works, and whoops, I had a little, I'm sorry, not integration by parts, but U-substitution works. You can do chain rule, you can do U-substitution, you can do product rule for derivatives, quotient rules, you can do integration by parts, you can do partial fractions, you can do power series, regular series, all kinds of crazy stuff. All right, but let's say, I'm running out of time, let's say that's all we're going to do for now, but if you want to take a look at some of the other stuff that we did, let's see, where did I put my blog? Oh, I lost it. But you can go to my blog in the top right-hand corner. You'll see I have some stuff saved there, some other stuff that we did. Okay, so that's it for today.